So today we start our last topic, which is bifurcation theory. This is chapter 12 in your textbook. We start talking about the bifurcation theory. Um, let's start with a simple example and give you guys the motivation behind this whole chapter here. This example presents a model for the insect outbreak. So basically, the Canadians notice that every once in a while, maybe 10 years, 20 years or so, um, there is this kind of a insect called spruce budworm suddenly may create an outbreak in the forest, which devastates the forest. But most of the time, it's manageable. But every once in a while, there's this serious outbreak that they simply can't control, and the budworm simply eats up the leaves in the tree, and a lot of trees will die because of this. So they try to create some simple mathematical model, try to understand this, um, and try to figure out what are the factors that matters the most in terms of controlling this budworm. So some mathematician came up with this um, simple population model where n is the population of the budworm. It has this logistic growth rate. So this term is the logistics term, modeling how fast the budworm is growing. And then the budworm, in most cases, is being eaten by birds. Okay, by birds. Birds, of course, also prey on other things, but budworm is a food source. So they use a predation term back here. So R here is the growth rate. K, as we know it, is the current capacity. P of n is the death rate of the budworm. This is due to, well, predation. So the P of n here, mathematicians are trying to model how this killing rate should look like. So let's think about how does this P of n look like to make it a little bit more realistically. N here is obviously the amount of budworm. Is the amount of the budworm. The predation rate, okay, this death rate due to predation, obviously should be increasing as n increases. At the same time, it's not going to increase exponentially or linearly without any bound, because even there are plenty of budworm, the bird may simply just had enough. They do not need that many budworms. So the death rate eventually will become kind of saturated at a steady level. So this steady level, we call it B. So this is the maximum. This is the maximum killing rate. Okay, this is the maximum killing rate because the birds simply don't need that many. And somewhere is the half killing rate, half of the maximum killing rate, B over A. And this is the critical population level that we call A. We call A. So this curve, okay, this curve is represented by the graph of this function here. So B and A are both parameters. B and A are both parameters. N is, well, the amount of budworm. So for this function here, you can easily figure out what happens when n goes to infinity. When n goes to infinity, P of n approaches B. Okay, approaches B. And also when n equal to A. Okay, when n equal to A. When n equal to A. What you have here is the predation rate will be A squared over A squared plus A squared, which is half of B, okay, which is half of B. So this is the critical population level where the predation rate is half of the maximum predation rate. So they use this. To model the realistic death rate for the budworm. So put them together. Here is how the population of budworm look like. Okay, this is how it looks like. The question is why there is this outbreak. Okay, why there is this outbreak every once in a while. What make the insect outbreak? Now, when we look at this single equation here, obviously there are quite a few parameters here. We have R, we have N, we have B and A. So these are all positive parameters. So one way that that we do commonly in analysis or in this ODE model here is we try to dimensionalize the system, sorry, the equation here, to eliminate some of the parameter here. So here we're trying to create a dimensionless equation here by introduce some new variable here. So we let x to be n over a. Okay, we're going to let x to be n over a, which of course is equivalent to n equal to ax. Okay, now x here is a function of t. Okay, x is a function of t. A here is the parameter in the equation here. So when you do n prime, it'll be, well, ax prime, and equals to the right side here. Okay, equal to the right side. R stays the same. N is ax. N is ax. N is ax. N is ax. So now you see the reason we're doing this. So we are going to eliminate the parameter a from this last term here. So now we're going to look at this new equation here. Okay, forget about this n prime here. So now we have this new equation about x prime. We're going to divide on both sides by b. Okay, divide on both sides by b. R over b times by ax divide on both sides by b. This is a squared over x squared, and we're going to divide the top and bottom by a squared. Divide by a squared, divide by a squared. Alright? So it turns out we can further eliminate some of the parameter by introduce a new time variable. We let tau to be the new time scale, which is b over at. Alright, so tau here is a new time variable. So we're going to do the chain rule here. dx dt, which is basically this x prime here, okay? This x prime is dx dt. It's dx d tau times by d tau dt. So that's the chain rule. dx d tau is, dx d tau is something we are trying to figure out. D tau dt, okay, d tau dt is b over a. D tau dt, because tau is a function of t, differentiate, you get b over a. So we're using this new time scale. So this a over b dx dt is the same as a over b. Now dx dt is this term right here. So I'm going to replace it with b over a. So now you see the reason why we introduce this new time scale, so that I can cross off this a over b, okay? Those two terms will be cancelled. dx d tau. The right side stays the same, okay? The right side stays the same. So those two terms cancelled. So you got this new equation with the new time scale. All right. So there are still 1, 2, 3, 4, still 4 different parameters in there. But now I can call this whole term, okay, which is r over ba. These are all different parameters from the original equation here. We're going to call this r. Okay, we're going to call r to be this guy. And a over k, I can further reduce it by letting a different k, so I'm using little k here, to be capital K over a. Then we arrive at the following new equation, which is much simpler and has just 2 parameters in there. Okay? So by doing this process, now we have this new growth rate R, and we have this new current capacity little k. So henceforth, we're going to study this one because it's simpler. It's simpler. Some of you may think that 2 variables is not a big difference, but it actually matters. Okay, it actually matters. So let's look at this new equation here. This is a new equation for the 1Budworm outbreak model. So let's try to think about the amount of equilibrium. The one equilibrium that we can easily identify is 0. Equilibrium. Alright, the one equilibrium I can easily identify is at 0. Alright, 0 means the 1Budworm extinct, which is very good, I guess. But how do we find out the other equilibriums? How do I find out the other equilibriums? Normally, I will set this right side equal to 0 and try to solve for x. But many of you probably noticed this is actually probably a polynomial of order 4, okay? If you set this equal to 0, multiply on both sides by 1 plus x squared, you're going to get a degree 4 polynomial. So figuring that out is kind of tricky. So instead of doing that, we can find out the equilibrium by finding out intersections between the two curves. Sorry, forget the x here. So this is the first curve. We're going to simply set it equal to the second curve. The second curve. Okay? So the intersection of those two curves will give us the other equilibrium. Obviously, I can also cancel out the x here because that's associated with the zero equilibrium. So we'll simply look for the intersection between this straight line and this curve, okay? X over 1 plus x squared. So let's take a look at what's happening here, okay? Let's take a look at what's happening here. This is a straight line. Let's take a look at this curve here. Take a look at that curve. Or 1 minus x over k. When x, so this is the x-axis here, okay? This is the x-axis. We're trying to plot the graph of those two curves. For this straight line here, when x is 0, the y value will be r. And when x is k, okay, when x is k, the y value will be 0. So this straight line, it is actually this straight line here. And then we try to plot the graph of x over 1 plus x squared. Let's take a look at this guy here. When x is 0, okay, when x is 0, it is 0. It is 0. And when x increases, this function value will increase. It will increase. So it'll increase. But many of you probably notice when x goes to infinity here, when x goes to infinity, this guy goes to 0, okay? Goes to 0. So it'll drop down. So this curve look like this. Look like this. Look like this. Look like this. So for this graph that I sketched, it appears that there is only one positive equilibrium, okay, one equilibrium. But you probably notice when I vary r and k, okay, when I vary r, for example, if I keep the k fixed, if I vary r, I may have different amount of intersections here. So now I will try to keep the k fixed, okay, I will try to keep the k fixed and show you a different scenario, okay, show you a different scenario and see what might happen. So I'm making a different sketch here. Let's say this is a typical curve. You can take out your calculator and plot a graph of this. So here is k. Here is k. The amount of positive equilibriums depend on r. Okay, if I keep k fixed. When r is small, okay, when r is small, there could be just this one positive equilibrium. One positive equilibrium. When you increase your r, turns out, okay, it is possible. So this is an algebra problem, okay, folks. It is possible that there are two intersections. So there are two positive equilibriums for r that's a little bit bigger. But there is also this scenario when r is even bigger, we may end up with So K here is the current capacity. Okay, K here is the current capacity of the budworm population. So in this case here, we have three different equilibriums. We call this A. So this is kind of a small number here. B is the number in the middle, and C, okay, the last number is something that's very close to the current capacity, and that is the outbreak level. Okay, that's the outbreak level. All right. So and then you can analyze the sign of the right side. Okay, analyze the sign of this guy here by comparing the difference between the straight line and the curve. So let's take a quick look. Okay, use the phase line analysis. Here is the x-axis, 0, A, B, and C. A, B, and C. So dx d tau. Okay, let's look at this term here. Okay, dx d tau on the left side of dx d tau on the left side of A, because the straight line. Okay, because the straight line is on top of the curve. The straight line is on top of the curve, so that difference will be positive. Dx d tau will be positive. So we use an arrow pointing towards A. Between A and B, the curve is above. Okay, this curve, this value is bigger. This value is bigger, so their difference is negative. We have an arrow pointing to the left. Pointing to the left. Between B and C, okay, between B and C, so once again, the straight line is on top of the curve. The straight line is on top of the curve. The straight line is bigger than the curve, bigger than this function back there. So dx d tau once again becomes what? Positive. Okay, become positive. So when somehow there are three equilibriums, this small amount is stable, B is unstable, and C is what? C is stable. So this is the outbreak level. Okay, outbreak level. So there are different cases here depending on this parameter R. Depending on this different parameter R. When R is very small, there is only one equilibrium, one budworm population that is manageable, that is close to 0. When R gets bigger, when you change your R, there will be two equilibriums. One is small and the other one is somewhat in the middle. When R further increases, okay, when R further increases, we can create three different equilibriums. One of them will be the outbreak level. Okay, one of them is the outbreak level. So the fact that the behavior of this system, okay, the behavior of this system depend on this parameter R. Depends on this parameter R. That deserves some study. So that's what we're study in terms of bifurcation. So the way that the behavior can change depending on one parameter, that's what we call bifurcation theory. Okay, that's what we call bifurcation theory. So once again, in this example here, for small r, there is one equilibrium. When you increase the r, somehow you can create three different equilibriums. So this kind of a change in the behavior of the system is what we call bifurcation theory. Okay, it's what we call bifurcation theory. So in our next section, I will talk about some basic bifurcation one-dimension equations, and then we move on to two-dimensional system. Okay.